time we discussed about continuous time martingale. Okay, and then as I told you, so what kind of results we have proved it for discrete time martingale that can be extended to continuous time, or say right continuous path of martingales in continuous time. So you have seen that I have already proved so-called the approaching inequality, and then Doops inequality, Doops maximum, or the LP inequality, we have proved it. Is it not? So if you see there, that idea is somehow you need to discretize in such a way, and then in a discretized form, one can form the discrete martingale or sub-martingale, and then you apply the known theorem, which is known from your discrete time martingale, and then you use the path continuity, in particular the right continuity of the paths of your given stochastic process, and then you conclude the same results which holds for discrete time martingale. No, that is actually we have seen it. So today, like in your discrete time martingale, what we know that suppose I have given you a submartingale xn such that supreme over n expectation over xn plus, that is the positive part of the sequence xn, it is L1, means bounded in L1. Then what we have seen there, then there exists a random variable, say x infinity, such that my xn converges to x infinity almost surely, not in L1 in general. Okay, and later on we have seen that so necessary and sufficient conditions for L1 convergence of a martingale or submartingale, that if it is uniformly integrable. So the question is, can we have a similar kind of result here, or the martingale convergence theorem for continuous time cases? And answer is yes. So this is given by this theorem. I am just going to state. So what it says that, so you have a xt, a stochastic process which is say right continuous martingale. Okay, xt is right continuous martingale, and C I am defining, which is supremum over t is positive, expectation over x plus t. Okay, exactly same conditions like in your discrete time martingale. Okay, then I am saying that xt, this converges to say x infinity almost surely, and my x infinity, which should be L1 of omega. Okay, so under this condition, so here also you see that supremum, it is uniformly, means it is bounded in L1, but only the positive part of your given stochastic process. Okay, so here I put as a martingale, but if you look at, if I just consider the submartingale also, then the result is true. Okay, so maybe consider the submartingale, then it is okay. So then I can find this x infinity is, I can think of, okay, there exists a random variable y such that x of t, as t goes to infinity, it converges to x of infinity. Okay, how to prove it? So proof is again using your approximate inequality like in your discrete type martingale. So what we have, that approximate inequality. So basically we try to show that if you look at the upcrossings as t goes to infinity along that path, then if that the number of upcrossing is finite, then actually, as you told, you know, like in even for the sequences, if you look at the upcrossings. So if it is finite, then sequence will converge. So the same idea is here. So what is your upcrossing? So if you have alpha and beta are two real number with alpha is less than beta, then what I know that for all n greater or equal to 1, you consider upcrossing on in this interval 0 to n, okay, alpha beta to x, and then take the expectations. What we have seen, this should be less than or equal to that expectation of x plus of, so this is basically what is the highest point here, n plus mod alpha by beta minus alpha. This part you have seen it, is it not? Okay, so now what I have already, I told you that this is the upcrossing, it is increasing in the set that if you increase your restricted path, then actually it will increase. In particular, almost surely I have un alpha beta, this upcrossing throughout the interval 0 to n, this should be less than or equal to u of 0 to n plus 1 if I consider over the same things. Okay, so it is a increasing, and hence actually what I can say, this part I have, and you see that expectation of 0 n alpha beta x of omega, this is less than or equal to this part. So now I can use basically the modern convergence theorem. So the pointwise limit, okay, I can say that limit or the pointwise limit n goes to infinity u 0 n alpha beta to x omega, this exists. Okay, so by modern convergence theorem, similar kind of argumentation we have used previously also. What we have that u 0 infinity throughout this path alpha beta to x omega, this is nothing but my limit n goes to infinity u 0 n alpha beta to x of omega, this is less than or equal to, okay, so basically I can think of that expectations of this part, okay, so then actually you can think of this is expectation of this part, and then you can put the inside things which is exactly here. So this part is less than or equal to whatever I have from here, these things. So now what I know that supremum over n, I know that supremum over any t greater or equal to 0, okay, expectation over x plus t, this is actually c, which is finite, and this is less than or equal to, I can have that expectation over x plus over any n, is it not? This part I have. So from here, if I just use these things and your this approaching inequality, then what I have from here, this is c plus mod alpha by beta minus alpha. Okay, so the expectation of this approaching is finite. Okay, and whatever that u0 infinity alpha beta x infinity over omega, this is greater or equal to 0 almost surely. So hence u0 infinity alpha beta x omega is finite almost surely, is it not? Because this is a non-negative random variable, expectation is finite, hence the random variable should be finite almost surely. Okay, so this is finite almost surely. So like in previous case, actually what I can consider, so define your a alpha beta, all those omega is in my omega, such that u over 0 infinity alpha beta x of omega is equal to infinity. And because of these conditions, what I have, probability of a alpha beta, this is actually equal to 0. Okay, and so now alpha and beta, now if I consider alpha beta from the rational numbers, and if I denote my a is this union over alpha beta is in my rational number, alpha is less than beta, and then a alpha beta, then probability over a, this is less than equal to summation over alpha beta, which is the rational number, and p of a alpha beta, hence it is basically 0. Is it not? So now, like in previously, in deterministic case, what do you consider? So like E, this denotes the event such that my x of t omega does not converge to a limit minus infinity to plus infinity. So then this E I can write down. I can write down that all those omega is in my omega such that my limit over t at x of t omega less than alpha, I can find alpha and beta real numbers such that these happen over t over x of t omega. Then use the upcrossing things, okay, by definitions of your upcrossings, and then you show that is, I'm saying that by constructions of upcrossing, so you see that this E, okay, so by construction of upcrossing, okay, so you can find that E is measurable subset of A. E is a measurable subset of A, I put it here, and hence that probability of E is less than equal to probability of A, which is 0. So what we consider that E is the event such that x of t omega does not converge to a limit in minus infinity plus infinity, and then the probability of that E actually is equal to 0. So that means, so in other words, what I have here, that almost surely omega is in my omega x t omega, or the limit t goes to infinity exists. So we denote as x infinity of omega, which is my limit t goes to infinity x of t omega. Okay, that means we show that as t goes to infinity, if there exists a random variable x such that it converges almost surely. Okay, so next we have to show that my xt, that x infinity, it is in L1. So for that, what we have, that expectation over mod of xt, these things actually I can write down 2 times expectation over x plus t minus expectation over xt, is it not? So now xt is your submartingale. So then what I can consider, that this is less than equal to 2 times supreme over t is greater equal to 0 expectation over x plus t minus expectation over x0. These conditions here, this is basically because of the submartingale conditions of xt, because my x of t is a submartingale. Okay, so because of the submartingale I have these conditions, and now this is less than equal to 2c minus expectation over x of 0, and this is basically finite because x0 is a submartingale, so this is integrable, and since I can write down this is less than equal to 2c plus the mod of these things I can have, so it is finite. So what it says here that if I give you that supreme over t expectation of x plus t is finite, means it is bounded only the positive part, then because of the submartingale and so on, I can say that it is bounded in L1. Is it not? That means basically I can say that supreme over t positive expectation over xt is less than equal to some c tilde. Is it not? So it may not be the same constant, but it says that it is bounded in L1. Is it not? Uniformly bounded in L1. Okay. So now you can use the Fatou's lemma. So by Fatou's lemma, thus by Fatou's lemma, exactly same argument we are considering here. What I have, that expectation over mod of x of infinity, this is less than equal to limit of n goes to infinity, expectation of x of mod of xt, which is less than equal to lim sup of, or not n, t goes to infinity, t goes to infinity, expectation of mod of xt, and this part we have seen this is finite, that is my x of infinity is in ln of omega. Okay, so like in I'm not giving here in example, you can find it find by you own one example that it converges almost surely but may not converge in L1. Okay, it's like in exactly similar things what happened for your discrete time martingale. Okay, because even the proof is exactly similar, one needs to just extend that things using the discrete case and then you prove it here. Okay, so in continuous set discrete setup we have proved the optional stopping theorem, is it not? So this can be extended for continuous time martingale or submartingale. So I am not going to prove it exactly in a similar way. So I just state this theorem, better to know this theorem, but proof, as I say, that one can extend it in a similar way. So that is called the optional sampling or stopping theorem. Okay, so what it says that, so let xt, this is where right continuous submartingale, with respect to the given filtration, say f of t, okay, and sigma less equal to tau, there are two stopping times. Okay, so then expectation x of tau given f of sigma, this is greater equal to x of sigma almost surely. Okay, this part we have, and in case of the martingale, so for a martingale, what we had, expectation over x of tau, that is actually equal to expectation of my x of 0. Okay, these are the cases I have. So now the similar kind of applications you can find out yourself, that if I try to find out my tau, which is the first hitting time of a Brownian motion, I will talk about the Brownian motion. just a few minutes later. Okay, and also we'll see that my Brownian component is also a right continuous martingale with respect to its own filtrations. Okay, and then this tau actually we try to find out, which is the first heating time. Then you will see that you can use the optional stopping theorem to find out this expectation of tau and so on. Okay, it is in a similar things like in your poverty case, no? Because in the gambling game, we have find out, no, that what is your tau. Either he means when he stop the playing, that either he gain all the required money or he loses, is it not? Whichever is earlier. And from there actually we try to find out what is the time, expected time, so that one can find out the expected time of the stopping the game and so on. That is why it's called the optional stopping theory. Okay, this is the case. I'm not going to prove it, but proof is exactly like in your discrete time martingale case. Okay, so now I'll talk about one important stochastic process that is called the Brownian motion. So what is Brownian motion? So I think in 1826 or 27, Professor Brown, he first observed the irregular motion of a pollen which suspended in a water. Later on, he and others, what they find out, that the path of a given particle which is very irregular, okay, and having no tangent at any point. And not only that, what they say that, what they observe, that the motion of two distinct particles, they are appear to be independent. So you have something like that, some zigzagness is there. Some zigzagness is there. Okay, so there is no tangent at any point. There is no tangent, or there is a tangent at no point. There is, okay, that's mean, and it's irregular, but you see that it is a continuous. So what they consider, actually they suspended a pollen in a water, and then they observe the motions of that pollen. So in a mathematically, if I give a description of these observed things, that is called the Brownian motion. Here is the definition. So, okay, in this case I am just considering the real value, but one can think of RD value and any space value things is there. So a real valued stochastic process we denote as Bt, t greater equal to 0, is called a Brownian motion if the following holds. Condition A, that B of 0 is equal to 0 almost surely. Start with 0 almost surely. Okay, sometimes it's called the standard Brownian motion. And then second is that Bt minus B of S, this is normally distributed with the mean 0 and variance T minus S for all T greater or equal to S. Okay, and third thing is that if you look at the increments, so that means for all times, say 0 less than t1 less than t2, so on, so on, and then you consider the incremental random variables, which is bt1, then b of t2 minus b of t1, and so on, b of tn minus b of tn minus 1, they are independent. Okay, so the random variables are independent. So now from here actually you will see that it has a stationary increments also because of the normal distributions and so on, and you see that it has a stationary increments. And D, that the central paths are continuous with probability 1. With probability 1. Okay, so basically what is the Brownian boson? Actually we see that it has independent increments, but here that BT minus BS, it has a Gaussian distribution or the normal distributions with mean 0, variance T minus S. This is more important, and it starts with 0. Okay, so since it has a Gaussian distribution, then in particular what I have, that expectation of B of t, this is actually 0 because B of 0 is equal to 0, so B of t normally distribution means 0 variance t, hence expectation of Bt is equal to 0, and expectation over B square t which is equal to t for all t greater equal to 0. Is it not? That is just from the definitions, because nt minus n of s which is normally distributed with mean 0 variance t minus s. Okay, and not only that, what I can have, that for any AB, for say A greater equal to B, what is the probability of A less than equal to BT less than equal to B? Because BT now you can think of as a random variable or normal distributed random variable, has a distribution with mean 0 variance t. So then actually I can think of what will be the probability between A to B, probability of A less than equal to BT less equal to B. So this is nothing but 1 by root 2 pi t integral over A to B e to the power minus x square by 2t of d of x. Okay. So this is for the single case. Not only that, we can find out the joint probability of this Brownian component as follows. So joint probability, what I try to say that if you consider 0 less than t1 less than t2 less than tn, and my a of I less than equal to b of I, where I is equal to 1 2 up to n, then the joint probability is given by the following formulations. So probability to joint probability means I am trying to say that what happened my B1 at B over T1, this is lies between A1 to B1, and then my B2 B at the point T2 lies between A2 to B2, and so on, that An less than equal to B of Tn less than equal to B of n. This is the joint probability. If I try to find out, this is one can give in this form with respect to the density function, which is A1 to B1, A2 to B2, and so on, An to B of n, and then you consider g of x1 t1 given 0, g over x2 t2 minus t1 given x1, and g over xn tn minus 1 given x of n minus 1, and then d of xn minus 1, d of x2 d of x1. What is my g over xt given y? This is nothing but 1 by root over of 2 pi t to the power minus x minus y square by 2 over t. Okay, this is the density. And then if you see that if you consider n is equal to 1, then a1 to b1 is exactly whatever I wrote down here. Okay, so this is the joint probability of the Brownian motion in this form. If you consider the time discrete points say 0 means t1 less than t2 up to t of n, and then we are asking what is the probability that b of t1 lies between an to b1, b of t2 lies between a2 to b2, and b of tn lies between an to bn, which is given in this integral form. Okay. Okay. So now if you remember I told you on sufficient conditions that when a stochastic process xt with respect to its own filtration gives a martingale, submartingale, and supermartingale. So there we have considered the expectations. No, if expectation of xt is equal to 0, then it is a martingale. Greater than 0, submartingale. Less equal to 0, supermartingale. So now, from that example, means one can check it, but without checking all these things, since we have done that example in a abstract setup, we can say that Bt is a continuous time martingale with respect to its natural filtration. Ft, which is sigma generated by B of S, such that 0 less equal to is less than equal to T. Is it not? This we can say, but one can also directly check it, but without checking this also I can say because of my previous example, which is in abstract setup. Okay, so one more remark I try to say, means there are many things you can consider. If I give you a Brownian component, a Brownian motion, so I can define more Brownian motion. In particular, suppose my Bt is given to you is a Brownian motion with respect to the given definition, say one dimensional motion, then if I define say yt which is equal to minus of Bt, then again it is a Brownian motion. Okay, and not only that, so now your t is fixed. I define y of small t which is equal to b of t plus capital T minus b of t. Okay, then you see this yt, again it is a Brownian motion. You just check it, all the conditions of the definition, it holds. It starts with 0 is equal to, sorry, b of capital T. Okay, it's a Brownian motion. So not only that, actually later on we'll have some strong Markov property for the Brownian components. So here I am considering T is deterministic and fixed, but one can think of T is any stopping time, and then B of T, which is T less equal to tau, it is independent of this Y of T, and also it's a Brownian motion. So that is called the strong Markov property. I will not go into that, but at least this one you can check it easily, that B of T plus capital T minus B of capital T, it's a Brownian motion. Okay, so here actually we try to, as I told you, we can, Brownian motion is a more important part in the analysis, in particular in stochastic analysis. It has a continuous path and the distribution is basically follows the normal distributions, and not only that, I can make from the Brownian component, which is a martingale, I can make another martingale, something like that. See, B square is a martingale. No, B square is a submartingale. No, B square T is a submartingale. So now I can think of the submartingale loops decomposition. What we know that submartingale things I can write down as a martingale and then plus some increasing process, is it not, with a0 is equal to 0. So that means I can find out, if I just subtract this at, that means my b square t minus at, it's a martingale. So if my bt is a Brownian motion or one-dimensional Brownian motion, then question 1, b square t minus t, okay, it's a martingale. Secondly, if I consider the exponential of sigma bt minus half of sigma square t for any sigma is in my real number, this is also a martingale with respect to its natural filtration. Okay, with respect to the natural filtration ft. Okay, how to prove it? So this one, the second one, this is really important. This is called the exponential martingale. I don't have time to do, but this exponential martingale has a many applications in finance. Okay, in financial mathematics, without this martingale theory, we can't go ahead. Okay, that has a many applications. So that is in a different subject in MTL 733. That stochastic for finance. That is the subject there, but there this exponential martingale play important role. Okay, but better to know that exponential martingale here also. Okay, how to prove it? So for the first one, as I told you that somehow I have a implication from Duke's decomposition that b square minus t will be a martingale. Let us try to prove it here. So I consider xt, which is equal to my b square t minus t. This is my xt. What I want to show? I want to show expectation over xt given f of s. This is my x of s almost surely. So this is actually I want to prove. No, TPT. Try to prove it. Okay, let's start with expectation over xt given f of s. This is idea is expectation over what I have b square t minus t given f of s. Is it no? So this part actually I can write down. This is expectation over b square t. I can write down bt minus b of s plus b of s and then whole square minus t given f of s. Is it not? I am just add and subtracting. And now why I am adding subtracting? Because I know that bt minus b of s, this is fs independent and b of s is fs measurable. That is more important, because if you look at how we have proved it, even for that example, there also we have using exactly same thing else, because xt minus x of s, they have independent increments as well as the stationary increments. From there actually we are having. So bt minus bs, I can have bt minus b of s, this is whole square, and then plus 2 of bs, b of bt minus b of s, and then plus b square s minus t given f of s. Is it not? I'm just expanding my square. So now conditional expectation is linear. Okay. So now bt minus bs is fs independent, and hence what I have, so I can write down this is that expectation over bt minus bs square, this part, and plus now b of s is fs measurable, so I can take out expectation over bt minus b of s given f of s. So now I am saying that this part actually goes to 0 because that bt is fs martingale, hence expectation of bt given f of s is equal to b of s, or otherwise expectation of bt minus b of s given f of s is equal to 0. And now b of s is fs measurable, hence I have d square s, and then minus I have t because t is the deterministic. And what is this part? So expectation of bt minus bs, this has the same distributions, means it is normally true to the mean 0, variance t minus s, and hence I have this is nothing but my t minus s, this part. Is it not? So t minus s plus b square s minus t I have b square s minus s. Okay, that is exactly x of s almost surely. So here I am using that bt minus b of s is fs independent, bs is fs measurable, is it not? And then the properties of conditional expectations. So this implies that xt, which is my xt minus t, is a martingale. Okay, let us prove the second one. So what is my mt or xt? I write down. Okay, I have not written down. So now xt is exponential over sigma bt minus half of sigma square t, where my sigma is a constant. Is it not? Sigma is in R. So to prove the martingale, first you have to show check that okay it is basically adapted and then integrable, but you see that actually it is adapted and integrable. You check it. How do you check it? So what is my expectation of e to the power sigma bt? You know these things, no? This should be 1 by root over 2 pi t minus infinity to plus infinity e to the power sigma s e to the power minus x square by 2t of dx, and then you see that it should be to the power minus half over sigma square t. Is it not? Is half of sigma square t, because bt is normally should mean 0 variance t, and from there actually you have this part. So this implies what is my expectation, because this is positive, by the way, this xt is positive. So expectation of mt, which is same as by expectation of mod mt, this is actually equal to 1 for all t. Okay, so it is integrable. Okay, so now if I choose my t greater equal to s greater equal to 0, then I know bt minus b of s, this is normally distributed mean 0 and variance t minus s. Okay, so if I use this similar kind of calculations, what I can have that expectation of expected e to the power sigma of bt minus b of s, this is exactly same as e to the power half of now sigma square t minus s. Is it not? Exactly, because bt minus bs is normally which means 0 variance t minus s. From there actually same calculations I can have. This is e to the power half of sigma square t minus s. Okay. Okay. So I have to prove expectation over exp sigma bt minus half of sigma square t given f of s. So exactly in a similar way, what I try to put it, I put it sigma bt minus sigma b of s. So what I can write down, this is expectation of exp of sigma of bt minus b of s, and then exp of sigma bs minus half over sigma square t given f of s. Is it not? This part actually I can write down. So now you see that this one b of s is fs measurable. This is constant because it is in deterministic, and so this is fs measurable. And then if you look at any Borel measurable function is there, so that should be also fs measurable. So it is fs measurable, so I can take out. Okay, so this is exp over sigma bs minus half over sigma square t, and then conditional expectation of exp sigma bt minus b of s given f of given f of s. Is it not? So now what we have to show? what we have to use here? See, Bt minus P of S is Fs independent. Hence, if you consider any, that f of, if x is independent to some, say, sigma algebra, then if you consider any Borel measurable function, then f of x is also independent of that. So if you use that part, this part is independent of Fs, and now use the properties of conditional expectation. What I have, this is the expected value. This is exp over sigma bs minus half over sigma square t, then expected value of exponential over sigma of bt minus b of s. We have already calculated this value, this expected value. So then from here what I have, this is exp over sigma bs minus half over sigma square t, and then exp over half over sigma square into t minus s. Okay, now that this is the product of exponential functions, from there you exactly have exponential over sigma bs minus half over sigma square, because this sigma square t plus minus got cancel out. This is sigma square of s. This is nothing but, if I denote x of t, then this is nothing but my x of x almost surely. Okay, so this is a martingale. And since it is a martingale, already we have done for a general case. Suppose my xt is, means this is not required here, but you know that if x is a martingale, then you consider the stopped process, then that will be again a martingale. And for a sub-martingale, it will be a sub-martingale. For super-martingale, it will be a super-martingale for the stopped process. Is it not? That means what I'm saying, that if you look at any, say, stopping time tau, then x of t minimum of tau, which is the stopped process, okay, so that will be a martingale, then exponential martingale with respect to that. Okay, so these are two important properties of a Brownian motion. Not only that, I have given you in your assignment that check that this is a martingale which involves the Brownian motion. Okay, so b square minus t I am having, so maybe already you have this bq minus 3b square t plus 6bt t square minus t, it will be again a martingale. Okay, you checked it in your in the exam assignment. I asked you to check whether it is a martingale or not. Okay. Okay. So as I told you that the Brownian motion, it is expected to have irregular path property. It is irregular. That means it has a tangent at no points. That means it is not differentiable. Okay. So regarding this path property, we will use so-called the Kolmogov's continuity theorem. We can expect that the sample path. So I can say the sample path property of Brownian motion. So what can you say about t goes to my b of t omega? Okay, for omega almost zero. This is the path property. So we can expect that it has uniformly Hölder continuity of exponent gamma, where gamma is less than half. Okay, I will show you how to show that. So for that, we will use so-called the Kolmogov's continuity theorem. I am not going to prove this theorem, but I will state this theorem, and then we will use this theorem to show the regularity of the path of Brownian motion. In particular, what is this Kolmogov's continuity theorem? Kolmogov's continuity theorem. What it says that, so now xt which is a stochastic process, say with continuous sample path almost surely. So actually this continuous sample path is not required, but anyway, so we can just write down such that this is something like that. I have expected value of xt minus xs if you consider 1 plus alpha. This is less than equal to, sorry, some beta. It is less than equal to some constant time t minus s to the power 1 plus alpha, where alpha beta are constant, positive, c is non-negative, t and s is greater equal to 0. Okay. So what it says that expectation of xt minus x to the power beta less than equal to some constant t of t minus s to the power 1 plus alpha. If satisfy these things, then what it says that x of t omega minus x of s omega, this is less than equal to k times t minus s to the power gamma. What is your gamma? Where 0 less than gamma less than alpha by beta, and t is say any positive number. Okay, this constant k depending on my omega, gamma, and then capital T. So it says that it is uniformly Hölder continuous with the exponent gamma, where gamma is less than alpha by t. Okay, that is the sample path, the t goes t x of t omega is uniformly Hölder continuous with exponent gamma on 0t. Okay, this is the Kolmogov's continuity theorem. Okay, this is Kolmogov's continuity theorem. Okay, so now we try to use this continuity theorem. In particular, if I choose say beta is equal to 2 of m. Okay, by the way, so for the Brownian motion actually I have defined you, and then what you know? What you know that if my x is a random variable with normally distributed with mean 0 variance sigma square, then if you look at the odd moment and then the even moment, okay, so all the odd moments are 0 and even moments we have some formulations for that. So here I just try to find out. So whenever say t is greater than s, what is my bt minus bs to the power 2 of m, for any m is a natural number. Okay, that means I am looking for the even moment. So these things are, this is nothing but 1 by root 2 pi over t minus s, because bt minus bs is normally distributed with mean 0 variance t minus s. So I have this is mod x to the power 2 of m e to the power minus x square by 2 over t minus s d of x, is it not? So now if you try to use the change of variable formula, this should be t minus s to the power m 1 by root 2 pi minus infinity plus infinity mod y to the power 2m e to the power minus y square by 2 over d of y. Okay, and we know that this is finite quantity because this is nothing but the even moment of a random variable which is now distributed with mean 0 and variance 1. So this is nothing but some constant time t minus s to the power n. Okay, so I put t greater than s. So then if you consider t is less than s, so that means I have to put mod, is it not? So what I have from here, that xt minus x to the power beta, this will listen to some constant t minus s to the power 1 plus alpha. So I have this m, so then I can choose my alpha is equal to m minus 1, is it not? Because m greater equal to 1, I can choose alpha minus 1. Hence by continuity theorem, Kolmogorov's theorem, hence by Kolmogorov's continuity theorem, what I can say that the sample path t goes to b over t of omega is uniformly Hölder continuous on say 0 to t for each exponent where gamma 0 less than gamma is equal to I have m minus 1 because by 2 of m. You know, that is alpha by beta. So alpha is equal to m minus m here, which is actually I have half minus 1 by 2m, which is still less than half. So that is why I say that with exponent gamma is still less than half. Okay. Okay. So now it is Hölder continuous with exponent strictly less than half. So the question is whether it will be differentiable or not. I don't know whether you know these things or not. So if it is differentiable, then it will be Hölder continuous with exponent 1, no? But it is less than half, so it is not differentiable. That is given by this theorem. So for each half less than gamma less than equal to 1 and almost every omega, if you look at the path t goes to b of t omega is nowhere Hölder continuous with exponent gamma. See, in the previous theorem we have proved, we have said that okay, it is uniformly Hölder continuous with exponent gamma. Okay, so that from the Kolmogorov's continuous theorem it does not say what happens if my gamma is greater than half, whether it is Hölder continuous or not. Is it no? So this theorem it says that if gamma is greater than half and less equal to 1, then the path t goes to b of t omega, it is nowhere Hölder continuous with exponent gamma. So if this is the case, then actually as a, okay, I will prove this theorem. So what is the consequence of these things? The consequence of this thing is the following, that the sample path of Brownian motion is nowhere. So the consequence of this theorem, one, that Brownian motion is nowhere, or the sample path of Brownian motion is nowhere differentiable. Okay, so that means basically the observations of Brown it basically satisfied, is it not? It is nowhere differentiable. No, there is no, means there is tangent at no points. It is nowhere differentiable. So why this is so? Because suppose it is differentiable at some point, say S0, then at that point BS0 would be Hölder continuous at that point with exponential gamma is equal to 1. But this theorem says that t goes to b t omega is nowhere Hölder continuous with the exponent gamma when gamma lies between half to 1. Is it not? So that means as a consequence of this theorem it says that the sample paths of a Brownian motion is nowhere differentiable. Is it not? Because if it is differentiable, then it is wholly continuous with exponent 1. But the previous means this theorem, then it's a contradiction to this theorem, no? Okay. And secondly, I am saying that the Brownian path is of infinite variation. Why this is so? Okay, there are two ways to prove this infinite variations. One is using the quadratic variation. So what is the infinite variation? So suppose in particular if you have, say, forget about your 0 to infinity, the time interval, suppose 0 to t. If you have a, say, function f, so we want to know what is the variations of, for the first variations of the function f. What you are considering, you are basically considering the partitions, say ti's are the partitions, then you look at f of ti plus 1 minus f of ti, then the take mod, and then take the summations over that things. So whether it is finite or not, with respect to when the partition length goes to 0, supreme over that particular we are considering. So this is the variation or the first variations of a functions f. So I'm claiming that the sample path of a Brownian motion is of infinite variations using the Beve's theorem. Why this is so? Now suppose it is of finite variation. Okay, suppose it is of finite variation. So suppose it is of finite variation. Then the path should be almost surely differentiable, no? Almost every are differentiable. But the previous theorem or the first consequence is that it is nowhere differentiable. So it contradicts the fact. Hence, the sample path of the Brownian motion, it should be of infinite variation. Okay. This is two important properties of the Brownian motion. See, the later on, that is called the stochastic integral. One needs to define something like that. Say suppose 0 to capital T x of t d of bt. So we want to define the stochastic integral with respect to the Brownian motion. Then what I know from the Riemann integral, how to define, means you cannot define these things as a Riemann Stieltjes sense, which is the classical sense. Means first maybe you can think of, okay, for every omega path or every omega I can define these things, but that is not possible because what we know that either if it is only of finite variation, then you can define this Riemann Stieltjes sense, but it is not. Or on the other hand, if it is differentiable, I can write down this is my b prime t dt and then x of t dt integral over 0 to t, and you can think of in terms of your Riemann integral form. But bt is not differentiable. So that is how it's a, means one needs to define in a little different way. That is the whole things of so-called the stochastic integral, or sometimes it's called the Ito integral. Okay, that is a different issue. I'm not going into that, but I just try to say these two striking property of Brownian motion, which is nowhere differentiable and of infinite, means path is of infinite variation, which prevents us to define the stochastic integral in a classical sense. Classical sense means in the sense of Riemann Stieltjes integral. So that is why you need a new concept, new theory to discuss about the stochastic integral. That is how there is a separate calculus called the Ito calculus, which is different from our deterministic calculus or the classical calculus, I can say, classical integral calculus. Okay, these are the two striking property here I want to show. Okay, I will not discuss about this stochastic integral and so on, and there are also other properties of a Brownian motions and so on. So one needs to find out the quadratic variation of a Brownian motion and so on and all these things. So I am not going into that, but at least you need to know what do you mean by the Brownian motion, what are the essential path properties of the Brownian motion which prevents to define the stochastic integral. Okay. So let us prove the previous theorem. What it says that if I consider the exponent gamma which lies between half to 1, then Brownian motion is nowhere Hölder continuous with that exponent. So proof for that. So now for simplicity we consider say t is equal to means small t lies between 0 to 1. So we consider for simplicity bt lies between 0 less equal to t less equal to 1. Okay. So now I can fix capital N such that n times gamma minus half, this is always greater than 1. Is it not? Because gamma half less than gamma less than equal to 1. This is given to you. So this gamma minus half is positive. So I can fix n such that that thing should be greater than 1 by the Archimedean property. Is it not? Okay. So now I am saying that suppose there exists a point S0 such that the path of the Brownian motion at that point is Hölder continuous with exponent gamma. So suppose, and then we try to find out a contradiction. There exists a point, say S0 lies between my 0 to 1 such that B of t omega minus B over S0 omega, this is less than equal to k times mod of t minus S0 to the power gamma for all t lies between 0 to 1. Okay. So I can set up the points in such a way that for large n I am setting I, which is n S0 box, which is the integer part actually I can consider, plus 1. This is my I, and then I am considering this point. So for j is equal to I plus 1 and I plus capital N minus 1. So now from this maybe star, what I have that I can consider B over j by n. So t I am looking from this j by n of omega minus B over j plus 1 by n of omega. So this j by n and j plus 1 by n, it lies between 0 to 1. So these things I can add and subtract of S0 point because I have these things. No, this holds for all t lies between 0 to 1. So in this setup, if I just consider, so now I am having from this number, no, I plus n minus 1 number point. So from there, what I have, this is my B of j by n omega minus B over S0 omega by triangle inequality, and B over S0 omega minus B over j plus 1 by n over omega. So these things what I have, this is k times the distance between j0 by n minus S0 plus mod over j plus 1 by n minus S0. Okay. So these things actually I can write down. This is less than or equal to, sorry, that should be gamma, some gamma. Okay, this is less than or equal to m times n to the power minus gamma. Okay, for some m, which is constant. I can always find out. See, j by n, how we find out this j, which is nothing but I to I plus 1 up to I plus capital N minus 1. So j by n, because if I just choose n large enough, then in this setup, I can always find out this j by n, j plus 1 by n up to j plus capital N minus 1 by n that lies in 0 to 1, and hence I can find out these numbers, these differences in this case. Okay. So you see this I lies between 1 to n and capital M is greater equal to 1. I am defining, so for 1 less equal to I less than equal to small n, capital M is greater equal to 1, and for large n, I define this set A M n of I, which is just looking at these expressions. Looking at this expression, I am defining that all those omega such that my b over j by n omega minus b over j plus 1 by n of omega, this should be less than equal to m times n to the power minus gamma. Okay, where j is equal to I plus 1 up to I plus capital N minus 1. These things. So what I'm saying, so now here this m is arbitrary. So in my previous case, m is fixed m for some m. Okay, so I'm saying, so now if a is a set of omega such that my b dot omega is say Hölder continuous with exponent say gamma at some point say s0, where 0 less equal to s0 less than 1, then this set A, it should be subset of union over m is equal to 1 to infinity, because it is arbitrary m, union over k is equal to 1 to infinity, intersection n is equal to k to infinity, union over I is equal to 1 to n. I lies between 1 to n, and a m n over I okay. This part actually I have. So for any set A is what is the A? A is the set of those omega such that B means the path of B is Hölder continuous with exponent gamma. Then A set should be the subset of my this set. Is it not? So now our claim is to show that probability of A is equal to 0. If I show that probability of A is equal to 0, then we are done. Is it not? That means basically that almost surely the path t goes to b of t omega is nowhere Hölder continuous with exponent gamma, where gamma lies between half to 1. This is the idea. So I have to show that probability of A, that is actually is equal to 0. So that means if I try to show that the probability of this set is equal to 0, then we are done, because it is a subset of that, and then by definitions of this A subset of B implies probability of A is equal to probability of B, so then it actually is equal to 0. Okay. So we show that probability over union over m is equal to 1 to infinity, k is equal to 1 to infinity, intersection n is equal to k to infinity, union over I is equal to 1 to n, a m n over I, this is actually 0. Okay, so now you observe this one. So probability over this is a constructive proof actually. Probability over intersection over n is equal to k to infinity union over I is equal to 1 to n a m n I. These things is limit of n, because you see that it is decreasing as n goes to infinity. Probability of union over I is equal to 1 to n a m n of I. Is it not? And now this is union, so I can have that summation. So this is less than equal to lim inf of n goes to infinity summation over I is equal to 1 to n probability over a m n of I. Is it not? This part I have. So now I try to calculate this probability of a m n I. So in AMNI, how it looks like the shape, this is all those omega such that this part, and then I need to calculate the probability. And what we know? We know that the if T and S, Bt minus Bs is normally distributed means 0. Hence I can have, so B over J by N minus B over J plus 1 by N. This is normally distributed with mean 0 variance 1 by N. Is it not? And it has independent increments, and hence b over j by n minus b over j plus 1 by n, where j is equal to I plus 1 up to I plus capital M minus 1, they are independent. Okay, so I am using the properties of a Brownian motion. So if this is independent, then what I can write down? The probability of a m n over I, this is nothing but I can write down, this is probability of b over 1 by n, that mod less than equal to m times n to the power minus nu, and then I have how many times? I have basically capital N times, because they are the independent. Okay, so I have this part, and now if you try to calculate this one, because this is nothing but this is nothing but probability over minus m n to the power minus nu less than equal to b over 1 by n less than equal to m times n to the power minus of n. Is it not? And then whole to the power capital N. So we know that how to find out this probability, no? So there if you see that it should be root n by root 2 pi minus m n to the power minus nu to m n to the power minus nu n to the power minus n x square by 2 of dx whole to the power n, and then you choose it. This should be 1 by root 2 pi integral over minus m n to the power half minus nu by m n to the power half minus gamma over e to the power minus y square by 2 of dy whole to the power n, and this is nothing but less than equal to some constant n to the power half minus nu times n for some c positive. Okay, you just check it. This is nothing else. For some n I have my this quantity. So thus what I calculated probability over intersection n is equal to k to infinity union over I is equal to 1 to small n, and then a m n over I. So this part I have, that lim inf over n goes to infinity summation over I is equal to 1 to small n probability over a m n over I. So now this is lim inf over n goes to infinity. I have this, all these things is bounded by this quantity, and then I have n times. So then what you have, I have basically c times n half minus nu over n into plus 1. So now these things is greater than 1, no? This part is greater than 1. Sorry, what we have? Gamma minus half. N times gamma minus half is greater than 1. and hence actually you see that the limit this is actually is equal to 0. Is it not? Because here half minus gamma, not gamma minus r. So you see that this is basically 1 by some n to the power some form. So as limit, so it basically goes to 0. So I have my this part, and hence and this relation holds for all k and m. So this implies probability over union over m is equal to 1 to infinity, union over k is equal to 1 to infinity, n is equal to k to n, sorry, k to infinity, union over I is equal to 1 to n, a m n over I actually is equal to 0, because this result holds for all these things when you have the summation over summation, is it not? Because all these things are summation over there, so you put k is m is equal to 1 to infinity, k is equal to 1 to infinity of probability of this part, and then you have 0. So this implies my probability of that set A actually is equal to 0. That means that it is no means for if gamma is less than, if half less than gamma is equal to 1, then almost every, and for almost every t goes to b of t, omega is nowhere Hölder continuous with exponent gamma, and as a consequence we have that the paths of a Brownian motion are nowhere differentiable and of infinite variation. Okay, so I'll stop now, and then maybe I'll start few applications of martingale inequality for the Brownian motions, and then I will start so-called the Markov chain. So in the next class I will talk about some applications of Markov or the martingale inequality to Brownian motions, and maybe half an hour, and after that I will talk about the Markov chain. Okay, I will stop now.
Excuse me, sir.
Yes.